Before we move on, I just wanted to look at an example calculation involving light and frequencies and wavelengths, just to help us get familiar with the equations that are associated with this. We're going to do a few calculations with light, not extensive ones, but a few. You should be familiar with it. And getting some practice with the units in particular, because the units here are a little bit different than units we've been using previously. We're going to have some units you've seen before, like joules, are going to show up again, but there'll be a lot smaller values than you're used to when doing thermochemistry, for example. So the example we're going to look at here is looking at a photon, or a light, with the wavelength of 532 nanometers. I picked this because it's a color of light that I think is really pretty. It's a green light that's emitted by lasers, several different kinds of lasers. It makes this really nice bright green color. So we're going to calculate the frequency of the light associated with that wavelength. If you have a wavelength of 532, what's the frequency? And then we're going to calculate how much energy a single photon of light with that wavelength of green light has. And then, for fun as well, if we had a whole mole of those photons, how much energy would that be? Because that's more relevant to, say, like thinking about a large scale process. Okay, so let's go ahead and do this. So the key to all of these is thinking about this equation here. So this equation that we've seen already is that the speed of light is equal to its wavelength times its frequency. So we know the wavelength, we know the speed of light because it's a constant, and so our only unknown here is the frequency. So we can just rearrange this equation. Frequency is equal to c over lambda, and just find the frequency that way. So we know the speed of light, we can look it up. It's 2.998 times 10 to the 8th meters per second. You don't need to worry about memorizing that. I will provide that to you on exams. Kind of like Avogadro's number. You'll become familiar with it just by using it, but it's not something you need to memorize. So that'll just go into the top here. And then in the denominator, we're going to put the wavelength. Now the wavelength is 532 nanometers, that's what we're told. But the value for the speed of light is in meters per second. So we need to make sure those units work out. So we need to convert nanometers to meters. So let's go ahead and do that. So 532 nanometers. And we need to remember that nanometers is 10 to the minus 9 meters. So that means there's two different ways we could do this. So let's say there are 10 to the 9th nanometers in every meter. And if we go ahead and plug that into a calculator, we will get 5.32 times 10 to the negative 7th meters. So we can go ahead and plug that into our denominator here. All right, and if we plug that into the calculator, 2.998 times 10 to the 8th divided by 5.32 times 10 to the minus 7 gives us a frequency of 5.64 times 10 to the 14. Now this is going to be in units of 1 over seconds, or the same thing is hertz. Okay, so that's our frequency, 5.64 times 10 to the 14th. The frequency is very large, so that's pretty normal for light. We get very large, very small values, very small wavelength, very large frequency. And those are inversely related because of this equation. Now the second question is, how much energy does a single photon have? Now the equation we need for this one is this equation that Planck and Einstein came up with, that the quantized energy, the amount of energy in a single bit of energy, whether for light or for matter, is equal to h times the frequency of the light. H here is Planck's constant, which has a specific value that Planck got from fitting it to the blackbody radiation, and this has since been measured to lots more digits than what we've got here. But we can just go ahead and plug this in. 6.626 times 10 to the minus 34 joules times seconds, and then we'll multiply that by our frequency, 5.64 times 10 to the 14 times 1 over, in units of 1 over seconds, or hertz. So those seconds are going to cancel, and we should just get joules at the end. So we can go ahead and plug this into our calculator as well. 6.626 times 10 to the minus 34 times the value I just calculated gives us 3.73 times 10 to the minus 19 joules. So a single photon carries very little energy, right? the values in joules we were calculating for heats of combustion and heats of were often kilojoules, and here we're like 10 to the negative 19 joules. One photon of light has very, very little energy. But what if we had a whole mole of them instead? That's the thing to remember about this calculation, is we're thinking about like one single photon. Now, if we have a whole mole of photons, that's going to be very different. So we would just take that 3.73 times 10 to the minus 19 joules. That's the energy per photon. So that's joules per photon. And we would just say, well, we have Avogadro's number in a mole. .022 times 10 to the 3 photons per mole. And so we can figure out how much energy would be in a whole mole of photons. So we take our previous answer, multiply by Avogadro's number, and we get 22.5 kilojoules, or 22,500 joules. Sorry, 225,000 joules. Or we could say that's 225 kilojoules per mole of photons. Okay, and then if we get a whole mole of photons, now it's on the same scale as sort of the energies that we were calculating with our reactions and things like that. And those were molar quantities too. We were thinking about moles. So this can help to make a more clear comparison between those values we were calculating in thermochemistry and these values we're calculating here. The main difference being that when we're thinking about one photon, it's a lot less energy than if we have a whole mole of photons. So that's some example calculations involving light, thinking about wavelengths and frequencies. And we can also apply this when looking at the photoelectric effect. So you also get some practice with using that equation too. But I just want to get a couple of examples for you to look at and to be able to see how you can do calculations here.